Hello, my name is Carl Goldman. I am the director of the U.S. Integrated Ocean Observing System Office, which is in NOAA in the National Ocean Service in the United States. Welcome to our session within the Ocean Observations and Sensing Track. This is a campaign and systems panel, and I am honored to have the privilege of being the moderator today and introducing the speakers to you. I'm going to introduce each of the speakers right now, and then we will run through presentations, and then we'll have some question and answer session as follow-up. So first off, we have Doug Wilson, who is an oceanographer and ocean and coastal observing expert. Doug has been in private consulting through his own company, Caribbean Wind LLC, since 2012. Prior to that, he was a research oceanographer with the U.S. National Oceanic and Atmospheric Administration for 30 years, and he is on the board of directors for the Mid-Atlantic IUCE region and a participant within the Caribbean IUCE region within the United States. And he was also founding chairman of IO-Carib GOOS, the Global Ocean Observing System Regional Alliance for the Caribbean. He's presently chief science officer for Ocean and Coastal Observing Virgin Islands, OCOVI, a nonprofit supporting regional ocean observing and he's also courtesy professor of marine environmental studies at the University of the Virgin Islands. Doug, maybe wave and say hello.
Thanks, Carl.
And next up, we have Lionel Camus, manager of digital solutions, Aquaplan NEVA. Lionel holds a PhD from the University of Plymouth. He has 22 years of experience in the impact of the oil and gas industry in the Arctic. He currently is manager digital solutions. Camus manages a fleet of surface and subsea gliders fitted with a suite of sensors for ecosystem characterization in biology, oceanography, and meteorology, excuse me. And so say hello and wave, Lionel.
Good afternoon, everyone.
Thank you. And finally, we have Paul Mathias, Senior Program Manager, Woods Hole Oceanographic Institute. And Paul has worked at WHOI for over 7 years as a Senior Program Manager and Chief Engineer. Paul has a BA and MS in oceanography and has a wealth of experience which covers satellite image data processing and display as a consultant to the U.S. He has experience which covers satellite imaging and data processing and display, and also as a consultant to the U.S. Navy, acoustic subject matter expert at Raytheon, leading design and development of human-computer interface, and acoustic element for U.S. Navy Zumwalt destroyer, and he has been an owner-operator of companies providing terrestrial, medical, and seafloor software and imaging solutions. How about a wave and a hello? Thanks, Paul. You are on mute. Just
hello. Good afternoon.
Very good. Thank you. So first up, Doug, you will be presenting, and why don't you go ahead and take over presenter privileges and take it away.
All right, thanks, Carl. My presentation is entitled International Hurricane Glider Missions in the Virgin Islands. I'm going to talk about the Virgin Islands, the Northeast Caribbean, and the wider Caribbean in general. So in the talk, we'll work our way through why the Caribbean, why the Northeastern Caribbean is important, some essential ocean features in the region we will be observing, and results of recent observing campaigns, and what we have planned for the future. My role here is as a Chief Science Officer of Ocean and Coastal Observing Virgin Islands. This work is done in collaboration with CARICOOS, the Caribbean Coastal and Ocean Observing System of IUCE, as well as Rutgers University Center for Ocean Observing Leadership, and there's a list of names there that have contributed. So a little about the Caribbean Sea. It's not just an isolated marginal sea. It's an undersampled pulse point for the global thermohaline circulation. Here's where the southern hemisphere and equatorial waters combine, move northward along the western boundary, and directly impact the processes of the islands they pass, and really contributing to the strength and variability of the whole western tropical and even subtropical Atlantic system of currents, and also the Western Atlantic tropical warm pool, which is the fuel that can rapidly intensify hurricanes. A lot of this discussion is going to be based on measurements in support of hurricane forecasting. So what I have here, I'll just start this up, hopefully. This is just an animation of total kinetic energy from satellite altimetry that shows the features, the essential features of Caribbean circulation. You can see coming in on the southeast corners, cross equatorial flow, North Brazil current rings. That's fresher water because of equatorial freshwater and river input along the South American coast. Comes into the Caribbean, really forms up into a very messy eddy-filled Caribbean current that then solidifies along the Yucatan Peninsula, becomes the Yucatan current, goes through the Straits of Yucatan, becomes the Gulf of Mexico loop current, the Florida current, and on into the Gulf Stream. So these are the features that really are critical. There's a lot going on. And again, it impacts the entire North Atlantic circulation. I'll stop that. So in the Caribbean, we're going to look at sea surface temperature as one of the variables, essential ocean features we're interested in. There's some long-term warming trends in that warm pool. This is the optimally interpolated SST, mostly satellite it is satellite from 1985 on, and by decades, and you can see the increase over time, over just 30 years. Here's what that looks like when you just pull out the trends. So this is the linear trend of at each 1 degree grid point. And you can see it's obviously increasing throughout time. What those numbers actually look like. So in the Caribbean wide mean here, that is an average of about 0.025 degrees centigrade per year, Celsius per year. The reason I've got two lines on this graph, this happens to be both the optimally interpolated SST and also the World Ocean Atlas surface temperature, because we're going to use the WOA 18 in order to look a little bit deeper. If we just look at hurricane season, you see that for July, August, September, October, the number's pretty similar, 0.03 degrees per year, but even a little higher. And in general, of course, that's about 2 or 3 times what we see over the global ocean. So in terms of SST, increasing. For hurricanes, we're interested in upper ocean heat content. That is the vertically integrated temperature above 26 degrees C, which is where supports hurricane growth. So it's a measure of the thermal energy in the upper ocean. These are just the two endpoints that we have, the 60s, 1965 to 1974, and then the most recent interval, 2005 to 2017. Again, these are in kilojoules per centimeter squared. Typically, you need around 60 to 80 is what we consider to be ability to support a storm. And you can see we go in the 60s from fairly, values that are close to that lower limit to quite considerably stronger values in the recent era. This is what that kind of profile looks like. This one is, you can see from that circle over in the along the Yucatan Peninsula, where that value actually goes up to around 240 kilojoules per centimeter squared, which basically is an upper ocean 200 meters of 29 degree water. This is the trend. It's interesting that we've got some hot spots in the Western Caribbean where this has been increasing. And again, if we do a linear fit, the black dots are the Caribbean wide. It's 0.62 kilojoules per centimeter squared per year. So we've gone from 50 to 80 roughly over this 50-year time span. Big increase. Another thing that's going on that we're going to look at, you saw the fresh water coming up from south of, along the South American coast from the equator. This is monthly values of salinity minimum. And so what you've got is a profile that looks something like this, where we've got quite a density gradient and essentially a lens of fresh water in the upper ocean. That complicates things because that too occurs during hurricane season, and it creates seasonal stratification that can limit vertical mixing. So we've focused recently on improving operational forecast for hurricanes in this Hurricane Alley region. And you can see why glider data are important, because we need to know these subsurface features, and we need to use those to compare to the ocean models that the hurricane forecasters are using. So in the Caribbean region, there are these critical upstream measurement points. There are these essential ocean features that we discussed. We need to have glider operations in that region to look at those, and we've developed those capabilities with some NOAA support, quite a bit of NOAA support and Rutgers support for glider operations in both Puerto Rico and the Virgin Islands. This is typical. This happens to be 2020, but these are glider tracks that actually are ongoing right now. They're representative of a typical season over the last 3 years since we've been doing this. This is an overlay of major US landfalling hurricanes that pass through the region. And you can see that what we're doing nicely covers that width of tracks. One of the problems, though, these are the exclusive economic zones in the region. And you can see that, again, it nicely covers the width, but it's pretty much confined to the US EEZs. There's one little orange track over there that's in the Dominican Republic through an agreement between NOAA and the DR. But in general, we would like to be able to extend up and downstream really from this region and begin to start collecting data in a wider range, particularly upstream, but quite a lot from a US standpoint happens downstream as well. So this is 2018. We began a program in the US Virgin Islands with 5 Navy gliders that we were able to deploy. And our goal in developing a glider program in the Virgin Islands with Ocovi and Caracas and the University of the Virgin Islands was to improve capability in the region, and also, as you'll see, improve our potential for future international collaboration. Those are the tracks, as you see on the left, of the 5 gliders that we had, and part of the group that we were able to train to do a lot of this glider work. This is just a figure that's based on those glider tracks that you saw. As we pointed out, as an essential ocean feature, we want to be able to look at heat transport, for example, into and out of the region. This shows that there is a discrepancy between the GOFS HICOM model that's used for hurricane forecasting and what we actually measured in terms of upper ocean heat transport. So we came back in 2019, in addition to supporting NOAA work. We went through the process of requesting research permission to work in the British Virgin Islands and Anguilla. We came back also with RU-29, the Rutgers glider sponsored by the Vetlesen Foundation as part of the International Challenger mission. And that's the mission sponsorship that's taken some of these Rutgers gliders across ocean basins and transatlantic and done a lot of work really supporting international partnerships in ocean observing. Try to get this right. So the white line that you see, that's our sort of iconic transport section across the Anegada Passage. And this is the glider track that we were able to do. This is leg 2. We did 2 of these type missions, winding our way through the seamounts in the British Virgin Island and Anguilla waters, and measuring water properties and transport here. I'll let that finish out. the glider died literally the day it left BVI waters into the US waters, so we picked it back up. This year, we're trying to extend that a little further, and what you see on the left there is a Eastern Caribbean wide picture of flow through those passages. This is some work that we did back in the 90s, and we actually were able to pin down those numbers. What we intend to do, starting probably early next year now, is send our U-29 down all the way down the upper part of the Caribbean islands. And so we have our marine science research requests in for all of these countries. And we've got the glider rigged up with what we hope is a little better ADCP and some other measurements. And this is our plan for this International Glider Challenger mission. Objectives to show the value of international cooperation in ocean observing. I mean, that's critical. It's also going to be a contribution to the UN Decade of Ocean Science for Sustainable Development. We've got cooperation with all of these countries through IOCARIBE. We'd like to do a better job of establishing protocols for glider mission cooperation, not have to go through the full Law of the Sea MSR process for each of these missions. We want to look at Caribbean inflow and interhemispheric upper ocean heat flux and water property climatology. Of course, improve intensity forecasts through collection and dissemination of real-time upper ocean data in hurricane regions. I didn't point out the important aspect of all this, which is that these data do go into a database and the global telecommunication service and directly into the ocean models for assimilation. Outreach to neighboring countries and establishing of continuing activities there. So I'm wrapping it up here. We continue to create capability, including local technical support and infrastructure. These are some of the things that we have planned, I think, or are considering this Vetlesen Challenger glider mission that I mentioned. This was the basis for a Rutgers University and partners, including everyone mentioned here, MacArthur 100 and change proposal. That's a $100 million proposal to have an impact. And indeed, that was not funded, but it was a good effort and a good way to bring together a way to create sustained observations, forecast improvements, education, societal awareness to lower hurricane risk throughout the region. We will, again, plan to be using this as a feature of the UN Decade of Ocean Science for Sustainable Development in the Western Tropical Atlantic region, and hopefully participate in a observing experiment coming up in the next year or two on NOAA extreme events observations. And again, it just makes the point that we clearly need expansion of ocean observations throughout the entire region. So with that, thanks. I want to send you all, everyone, to look at this Ocovi YouTube channel. There's an absolutely awesome video of glider operations. You don't get this blue color anywhere else in the world, and it's a striking visual images. So thank you, and thanks, Carl.
Thank you, Doug. And now, Lionel, you should be moving to present on your screen. I'm tempted to jump into questions, but I'm going to pause and not do that yet.
All right, can you see my slides, Doug?
Yes.
Yes. Okay, I'm trying.
You're not in full presentation mode yet.
All right, it's coming. And then I will activate my pointer in case I need it. All right. Okay, good afternoon, everyone. So my talk is about using glider vehicle, different type of glider vehicle to reveal new discovery in the Arctic in terms of ecosystem understanding. And it's part of a project which is financed by ConocoPhillips and the Research Council of Norway. So it's a program which has been running now for the last 3 years. And I will also tell you more about 3 years continuation of the project. We market the project with a very basic name. We call it Glider and Man Ocean Exploration with this logo. So you might find this from time to time in press releases and in the national news, especially in Norway. So briefly, the partners, this is a project where we have quite a substantial number of partners. All of them are based in Norway. So you have the Norwegian Institute for Water Research, NORS, which is one of the largest technology institutes in Norway. The Norwegian Meteorological Institute, Kongsberg, which at the time of the project was still owning and fabricating the sea glider, which has been now passed on to other companies. Onderaf, a sensor company, Offshore Sensing, which is a Norwegian company that fabricates a surface glider. Maritime Robotics, which operates for liquid robotics, the wave glider. And then we have academic institutes like universities in Tromsø and the University of Bodø. So we have a constellation of very of complementary institutes, providing sensors, technology, managing digital data, but also looking at data to produce some science. So the motivations of the project, basically it's to pretty much bring disruptive technologies in the Arctic. And why we want to do that? This is today pretty much the main mandate that the European Union has. They would like to unlock blue growth in the Arctic. So a little bit of text. Basically, at present, Norway, the EU, the academia, and Arctic stakeholders and global economic actors have insufficient shared knowledge and common platforms and access to human capital to respond to the need for Arctic stakeholder participation. In Northern Norway, we have very, very few people and very few research institutes. And within 30 to 50 years in the future, Europe and Norway foresees, economical growth in the Arctic. And in order to do that, we need to find, solutions to generate knowledge into this ecosystem. Otherwise, the situation threatens the legitimacy, social license to operate, competitiveness, and feasibility of new economic activities, even when these have the potential to be just desirable by all parties. So having considered this, what is our vision? So basically, it's to utilize gliders, glider vehicle, which, as a fleet could be deployed in the Arctic in some selected location of interest to collect data near real time to generate science and to cover gap of knowledge. So in order to do that, we have assembled hard and soft technology. Basically, in a nutshell, our motivation was to look primarily towards biology, ecology, and physical oceanography. So we want to understand better, again, the ecology of sea mammals, which thrive in the Arctic. Fish stock, the Norwegian Arctic has one of the best managed fish stock, which is the Northern Atlantic cods. Of course, krill, fish larvae, you have, it's a place as well where you have fish spawning, especially on the northwest coast of Norway. You have as well specific sites where you have super aggregation of plankton like copepods, and we wanted to understand why and what caused this and what is the advantage for the fish to have this super aggregation of fish. And of course, we want to understand better algae and physical oceanography. So we have assembled a set of different sensors from hydrophone, ecosonder, the one of Simrat, the EK880 with a 333 kilohertz transducer. We have CTDs, ADCPs for ocean currents, fluorometer, and a lot of additional sensors to look at oxygen, CO2, turbidity, and CDOM. These are the glider that we have selected. So we have actually one sea glider from Kongsberg. We have several sailbuoys fitted with EcoSonder, ADCP, and we are currently developing new sensors to increase the number of functionalities on board the sailbuoy. And then we have also a wave glider in which we have also integrated quite a large set of sensors. In order to manage the fleets and the data that are generated by all the sensors, we have fabricated a digital platform, and I will let you know about this later. But basically, that was really critical to have a platform which is really addressing all of our needs, not only to operate them, the gliders and the sensors, but to really be very professional in the data that we collect, making sure they are collected and stored according to the Copernicus European system in terms of database and units and so on. So basically, we have developed this tool, to again, to liberate the data, generate applications, and potentially support innovation. So the data management platform, I will show you just the basics, the different components. Basically, we use the Cognify platform of Kongsberg Digital, and this digital platform Cognify is at the crossroad of the module of the data quality control that is developed and operated by NIVA. And these algorithms are based actually on the requirements of the European system Copernicus. And we use the Microsoft Azure cloud to store the data, both the raw data, QC data, and analyzed data. So in order to visualize the data, we have also developed our own web-based portal. So this was developed together with our scientists to make sure we provide, we fulfill their needs. So they gave us a lot of recommendations on how they wanted to visualize the data, and also how they wanted to extract some of the data which were of interest. And further, we developed a couple of applications, especially for oceanographers, where we have actually coupled all the data stream into existing model near real time to calibrate model in near real time. So the objectives of the project, in brief, what we wanted to do is to collect high-resolution data sets in space and time, in near real time, in marine ecology and physical oceanography using glider in the Arctic. So we want to enhance ecosystem knowledge. We want to improve as well model forecasts, and at the end, ultimately, environmental management practice. And of course, there is ultimately a vision for providing such a concept for our stakeholders and also customers, such as ConocoPhillips. So what have we achieved? 2 years ago, in Ocean International, I have actually presented the project that was freshly started. So now I will present you some of the survey we have carried out and some of the data that we have collected. So we went to northern Norway, above the polar circle, especially in a specific location where you have a lot of interest from a lot of different stakeholders, like the oil and gas industry, the fishermen. You have a very intense fishing fleet there. And of course, you have as well very specific biological features. This is where most of the fish living in the Arctic come to spawn every year in springtime. So you see the track on the screen of the different gliders. And along with this track, we had as well ground truthing, which were performed with different research vessels. So we had some waypoints where we agreed to run the gliders in parallel to the research vessel, which were collecting fish larvae, zooplankton, and looking at different parameters, again, to ground truth the EcoSonder data or some other type of data that we were collecting. So this deployment was a 6-month deployment, and that's also something we wanted to achieve, to test the performance of both the platforms and the sensors in this specific region in the Arctic, especially when you have not so much sunlight in the winter. Last year, we have performed 2 additional surveys. So one all along the west coast of northern Norway, from Trondheim all the way to pretty much Tromsø. And as you can see, each glider vehicle was allocated a very specific survey with specific research objectives. And then later in the summer 2019, we really went into the high Arctic in Svalbard, on the west coast of Svalbard. So we deployed the sailboy and we went all the way up to the ice edge and back again. I will now show you a couple of results to show you the benefits again of using this glider. Many papers have started now to be drafted, and the first one was actually accepted this summer. So this is still, very fresh in terms of data analysis and interpretation. But basically, I also wanted to show you as well how we visualize our data using the web portal that we have fabricated. So this is the sea glider, which and the data that relates to the fluorescence. So basically, this is chlorophyll A. And you see the track from the west coast of Norway all the way down to the deep water, about 1,000 meters. What is interesting there is to see in green the fluorescence, which corresponds to the chlorophyll A. And you can see there that you can detect chlorophyll A all the way down to 500 meters. So basically here you have a very strong current, which is basically the Gulf Stream, that brings chlorophyll A from the surface down into depth. And this generates a very specific ecosystem there just at the start of the continental slope. And you will see later that may just explain as well some of the findings that we do a bit later. And like the previous talk, it shows again the complementarity between the satellite information that would give us information on the ocean color at the sea surface, but will not be able to resolve the deep water. And this is what the sea glider is capable of telling us. On the next slide, this is the echogram that has been collected with the sailboy fitted with the echosonder EK80 from Simrad and the transducer 333 kilohertz, which allows us to target small creatures like the copepod, you see about 1 millimeter size, and also the fish larvae. The echogram that you see there, basically, that's the condensate of this track, starting from Bodø, crossing this fjord and going on the west coast. So the white patch that you see, this corresponds to this copepod super aggregation. So we call it really super aggregation because if you see on the satellite picture, we're capable of detecting the pigments of this copepod at the sea surface, because as you can see on this echogram, they are within the first meter of the sea surface. So what is unique there is that this sailboy does not disturb this aggregation of the copepod, unlike if you had a research vessel. Both the light, the noise, the instrument station, and the fact that the transducer is located at the bottom of the hull would prevent you to see this aggregation. You would start to collect data probably from 20 meters. And as you go further, using different softwares like EcoView or other type of software, you can also extract this dynamic of these patches, with this daily migration of these organisms into the water column, and also to try to semi-quantify the biomass of these organisms depending on depth, depending on the time of the day, and so on. Now we are very much interested using to integrate this ecosonder into the sea glider to really understand the dynamic of this population when they hibernate in deep water and when in the springtime they start to ascend into the water column to feed at the sea surface. So this is one of the next objectives that we have in this region. Of course, we looked at top predators using hydrophone. It appeared that the sea glider was actually a very nice platform, very quiet, so we could really listen carefully without disturbing the sea mammal like a ship would do. So these are the different species that we have identified, and very surprisingly there we detected sperm whale, and this is the first time that sperm whale has been recorded in this region. So you have, a lot of surveys looking at sea mammals in Norwegian waters, and sperm whale have never been detected there. And it appeared that when we looked again at the topography of the seafloor, we saw that this sperm whale was detected in a very small canyon. And this is within this canyon that the sea glider as well, detected this presence of phytoplankton that was brought on the seafloor, probably, generating a specific ecosystem where the sperm whale can find food. So again, this platform, which is very quiet, non-invasive, allows us to make these discoveries in this ecological system. Of course, we recorded anthropogenic noise, and we are now working on the soundscape to understand better the tentative impact of this noise, at least to characterize it, whether it is seismic activity. As you know, Norway is an oil country. You have a lot of oil and gas activities, such as seismic. You have as well a very intense shipping lane connecting Russia to Europe. So you have a lot of boats running along the coast. We can also measure the noise of an oil and gas installation. This one is Asta Hansteen from Equinor, which is in deep water. Maritime traffic, so we record the noise of the propeller, engine noise, whether it is a cargo ship, whether it is recreational or fishing. And also research. Research does a lot of noise. This is here a deployment of a subsea observatory, which is deployed by the Institute of Marine Research. So we sent the glider over there, and we saw that we were capable of recording all the activities that they were having there to connect and deploy their new facilities. So we are currently as well working on whether these different noise have an impact on the sea mammal ecology, especially on their vocalization, but also on what is their behavior with regards to the presence of this noise. Physical oceanography, what we have done is to collect, as you can see on this screen, you have the track of the sea glider for one full day, 24 hours. And these data were assimilated into the ocean model of the Meteorological Institute, so that is used, for weather forecast. And basically, the simulation that you have here indicate with a strong patch at the same location where you have the glider, that the model has been significantly recalibrated. And this one is about salinity, and we did as well for temperature, where again you have the glider track for 24 hours. And then we assimilate the data in terms of salinity into our model, and we see this very dark patch, which indicates recalibration of the model that was significant. And then once we have done that, we have embedded our high-resolution model that we call FVCOM. The coastline of Norway is very complex. A lot of fjords, rivers, a lot of freshwater input, a lot of islands, and therefore existing models, which are most of the time about 1 to 2 kilometers resolution, are not enough to resolve what's going on in terms of movement, water masses. So therefore, we have developed this high mesh resolution of model, all the way down to a few meters, and this is on the same coastline an example of what we get in terms of resolution. This is on the bottom the ocean model that the Meteorological Institute in Norway operates, and on top, this is the high resolution model that we have fabricated and applied there, and which is also recalibrated thanks to the glider data that goes into this METNO model. So basically now, in terms of oceanography, we have an excellent tool where we can generate a lot of different type of application depending on stakeholder needs for this geographical area. So what were, in brief, some of the added value of the project that we have been running? The first one is that definitely gliders are non-invasive, unlike research vessel. What, together with Tromsø University, what we now have identified is that a large proportion of the data which have been collected, for the last decades, on zooplankton, maybe fish larvae and so on, are actually biased, and largely biased, because the ship will not give you information on the first, let's say 10, 20 first meters, and therefore you have the tendency to forget about what's going on in terms of dynamic and processes in these surface waters. But also the light, the noise, the vibration move animal away tremendously. And with gliders, you are completely non-invasive, non-disturbing. Therefore, you can really collect a high-resolution type of understanding of this ecosystem. I talked about disruptive technology. It is very clear, considering the amount of information that we have collected, that the quality in terms of data and resolution is there. Most of the data were near real time, or actually real time. So the scientists get the data on their desk and they can work on the data right away. So it's very efficient. We have reduced our cost dramatically. Basically, we have not sent people on the field, and gliders were deployed for up to 6 months. And then finally, we see that this is a very green technology, unlike deploying research vessels, which consume hydrocarbon. So basically, to conclude, in relation to the stakeholders that we work for, we see that gliders can cover a lot of different types of themes, from physical oceanography, real-time assimilation into model, getting an understanding in ecosystem structure and functioning. We also managed to address the biological components, which often were poorly addressed by gliders. One of the intention, of course, as well, is to look further into anthropogenic impact. So we're doing it for noise, but we will also, as well, in the future, look at pollution from different sources, etc. So basically, we definitely have an enhanced ecosystem understanding when we deploy such technology, and that allows us to really, have a lot of type of application for an enhanced and improved management practices. I will conclude as well with giving you a snapshot on the continuation of this project. For ConocoPhillips, we will continue working for the 3 coming years, and we will actually now work closer to the oil and gas installation, since they're interested now to deploy this vehicle and the concept around Ekofisk, which is one of their largest oil and gas platform in the North Sea. And we will look at the impact of seismic activities, especially at the ecosystem level in an integrated manner, and also looking at the impact of produced water on the marine ecosystem. So this is, and the third objective, and not the least, is really to turn this glider concept into an operational tool that the customer can also use. So for instance, this is the digital twin of Ekofisk, and I have represented our glider vehicle there and there. So the idea is really to get there and get close to the customer, so that all these vehicles, the sensors are also embedded into their operational system. Okay, I will stop there. This was the glider project in a nutshell, and of course, along with that, there are a lot of new sensors and functionalities that we are fabricating or developing, and I hope that there will be some more conference in the years to come where I can present these new functionalities and gliders activities in Aquaplaneta. Thank you very much.
Thank you, Lionel. That was excellent. And next up, we have Paul. And so you should take over presenting rights.
Yep. Thanks, Carl, and thank you, Oceanology International, for the opportunity to speak. I'll be here talking about the Ocean Observatory's initiative. It is a National Science Foundation funded program. It is a NSF, United States National Science Foundation major facility. And a major facility is a facility that has significant construction costs across many years, typically between about $100 million and $800 million. There are today 33 major NSF facilities across the country. With OOI, the construction and initial operations began in 2009. The OOI is kind of a new paradigm for at least a portion of oceanography, in that it shifts away from short-term, expensive campaign-style observations collected by a small group to long-term continuous measurements that are available in near real time to anyone with an internet connection. So scientists, researchers, and educators worldwide have been using OOI data for analysis, publication, and education. The OOI 2.0, or the next instance of OOI, began just 2 years ago in October 2018, when Hui took over the leadership of OOI and is working today collaboratively with University of Washington, Oregon State, and Rutgers on delivering data from the infrastructure. So what is the OOI? It's a system of systems. The individual systems or observatories shown here in the world map exist in the southern and northern hemisphere around the Americas. There's the Pioneer and Endurance arrays. These are the coastal arrays on the east and west coast, respectively. The Global Erminger in Greenland Sea, and Station Papa array in the Gulf of Alaska, and the Global Argentine and Southern Basin arrays in the southern hemisphere were suspended in 2017 and 2020. All of this infrastructure is delivering data from 75 platforms, about 770 science instruments, and that measurements from these platforms are being gathered, stored, processed, displayed, and served through the cyber infrastructure. The observatories range in water depth from about 25 to over 5,000 meters. And each of these arrays is visited either once in the case of the global arrays or twice for the coastal arrays, and fully replaced with a refurbished set. So there's two alternate sets, one that's deployed and operational, the other that's being refurbished, that provides for continuous 365-day, 24/7 data delivery from this infrastructure. The OOI is multidisciplinary in that it provides, has instruments and provides measurements from geology, chemistry, physics, and biology. And the data is entirely uncabled, or the instruments and infrastructure is entirely uncabled, except for the tectonic focused array off the west coast. The main science themes of the OOI are the ocean-atmosphere exchange, climate variability and circulation, ecosystems, turbulent mixing, coastal ocean dynamics, and plate scale geodynamics. So as an exemplar, this is one of the arrays, the Coastal Pioneer Array. As I said, there are 7 arrays in total. The Coastal Pioneer Array is laid out in a rectangular pattern, where we see in this 3D image, there are 10 moorings that are fixed to the sea floor, arranged over the continental shelf break, which is the science focus for this array. There are several components here to note. One are the gliders and autonomous vehicles. There are 6 gliders that encircle the array and run on what we call a racetrack pattern, repeating again and again the same tracks to provide for long-term observations from this region of oceanographic phenomenon. There are the 3 large surface moorings with large surface buoys identified here in the upper right corner. The surface buoys carry a full meteorological suite in addition to the oceanographic instrumentation, and also generate power in a green way from 2 wind turbines, 4 solar panels, and a bank of batteries. The profiler moorings that complement the surface moorings carry wire following profilers And on the bottom, we see the multifunction nodes. These are raft-like looking like structures that provide for a base right on the seafloor for instrumentation. There's a total of 110 instruments collecting measurements from the atmosphere to the ocean floor at the Pioneer Array site. There is an intention, by the way, to relocate the array through an NSF-led process in about 2 to 3 years. It was always the intention for the Pioneer Array to be a movable one, to be relocated somewhere else to study another different region of the oceans. So since OI 2.0, we've delivered enhancements to key program areas for process improvement. These include management, community engagement, data delivery, and engineering. In management, we created some new and redefined some existing program management team roles. We've developed a tool for performance-driven decision-making. So to be able to drive decisions through analysis of alternatives and quantitative trade studies has provided us with a way to build consensus for decisions and develop and deliver a defensible decision for changing instruments or instrument positions, for instance, or relocating components of the infrastructure. In community engagement, we've hired and filled a community engagement manager role. We've really dove in the last couple of years into social media, providing opportunities to connect through LinkedIn, Twitter, and others. And also delivered a new oceanobservatories.org website. So if you had been familiar with oceanobservatories.org in the last several years and haven't visited it, it's worth revisiting the website to see the changes that have been made. In data delivery, we've embraced quality assurance, quality control of real-time oceanographic data, or CORTOD. That's a tool developed by and managed by NOAA, which creates a set of authoritative QA/QC procedures for oceanographic instrument data, which is becoming more and more a global standard for QA/QC. And finally, in engineering, we've commenced a series of data-driven reviews, established a process for technical refresh. On receipt of instruments and components, we conduct a documented set of quality conformance testing, and finally established the important performance metrics, which allow us to assess performance of the infrastructure and make modifications, improvements, or enhancements as needed to improve that performance. So this is a very high-level representation of performance metrics from last year, from 2019. So for each array listed down the left side, in one column, we have number of science sensors. In the AWP, that's the annual work plan. So these are this number of sensors that were planned to be deployed to that particular array. The next column is the number of science sensors actually deployed. There may have been an issue with an instrument just before deployment that causes this number to be not as high as the number of science sensors planned. And then the expected science data column indicates for the number of science sensors that were deployed, how well did they perform? Did they deliver data 100% of the time or less than 100% of the time? And in most cases, you see here, 80% or above is pretty good for deploying oceanographic instrumentation without intervention for year-long intervals on both fixed and moving platforms. Some of the reasons for less than 100% expected science data could be instrument failure, a platform failure, or a data path issue. And it's our aim, and it goes beyond the scope of this presentation, to dive into each of these statistics for details that are behind them to better understand root cause and corrective measures that can be made. So the metrics lead us to focusing on weaker areas of the program that we are actively enhancing. So the continuous improvement process, we could say, is aimed at two main objectives. One is delivering data to the end user. The other is ensuring long-term operations. The OOI is intended to operate for a 25-year lifespan. And so continuing to address obsolescence issues, vendor quality issues, and any potential failure modes is a very important part of the management of the OOI. For data to the end user, we evaluate sensor performance through data-driven reviews, and we've begun those data-driven reviews last year. I'll talk a little bit more about those. In the long-term operations, we have developed a technology refresh plan that evaluates based on a series of criteria, including vendor quality and looking at alternatives and reviewing system and instrument requirements. We're constantly evaluating opportunities to refresh the technology and enhance it to deliver even higher levels of performance as we go forward. So what are the data-driven reviews? These are quarterly or every 3 months. The first one was in December 2019, where the focus was on the sensors and the sensors that exist on the OOI program, over 800 instruments in total. The inputs were across MIO groups, so working with our partners at UW, Rutgers, and Oregon State, we established an instrument working group and identified a set of qualitative ratings that highlighted certain instruments that were performing better than others. The outcome from the data-driven review in this instance were a set of quantitative analysis techniques. We updated the requirements that correspond to the instruments based on true, actual empirical performance, developed a technology refresh procedure that we've been employing ever since, and prioritized instruments for close evaluation and consideration for replacement and improvement. So the continuous improvement today, again, the quarterly driven reviews, the performance metrics, which range from platforms through components and specific elements of the infrastructure. The OOI has also established a set of working groups for evaluating sensor performance, the gliders, data processing specifications, including CORTOD, and sensor technology refresh. So on this page, I've just provided a list of access points. The main Ocean Observatories page is oceanobservatories.org. Here you can see information including technical data packages for all the deployed infrastructure, news, the webinars, and most importantly, perhaps of all the data that's been collected from all the instruments of the OOI is available through a new interface, the Data Explorer tool that was just released this week. It can be accessed here at the oceanobservatories.org. The Interactive Oceans tool developed by University of Washington provides for an enhanced user interface to the specifically cabled array interface, including real-time video from a live seamount. The Ocean Data Labs tool developed by Rutgers it provides interactive OOI data explorations and data lab notebooks for educational purposes. And NSF does not fund science through this OOI program that I manage, but rather provides for science funding separately from time to time through their nsf.gov website. There are a series of webinars coming up next year, including a biochemical sensor workshop at some time in 2021. And we're always looking for feedback, partnerships, and collaborations. So in conclusion, there are a series of opportunities to interact with OOI and take advantage of this large major facility investment by the U.S. National Science Foundation. You can use the data through a number of interfaces, including machine-to-machine interface and ERDAP. ERDAP is a data server that provides a simple, consistent way to download subsets of gridded and tabular scientific data sets in common file formats. You can propose to modify the sampling, gliders, AUVs, or instruments. You can add instruments to the OI platforms, either self-powered and take advantage of the deployment and recovery cycles that we operate. You can add platforms to the array site or supplemental vehicles. And we also welcome opportunities to work with others on our OOI turn cruises that operate throughout the year. And finally, as I mentioned, the potential Pioneer Array move will commence with discussions across the science community in the fall of 2023. So with that, I'd like to conclude and thank you very much for your attention. And I'll turn the floor back over to Carl.
Thank you, Paul. Excellent. 3 excellent presentations, and we're going to have some time for question and answer. I want you all to be able to ask each other questions as well. I'm going to kick off with one question that I'll then ask each of you to reply to, but then we can get into some more back and forth exchange, not too formal. So my first question is that our track is called Campaigns and Systems. So I'm curious for each of the panelists to say a few words about what makes your topic that you presented on today. Does it fit into a campaign or a system or both or other? So Doug, how does your work with the hurricane gliders, how is it a successful model for advancing operational oceanography as a campaign or a system?
Yeah, I mean, I see it as a campaign. I think we had an initial goal of improving hurricane forecasts. We looked within a region that we thought was important, the Caribbean. We looked at the essential ocean features that contribute to, say, hurricane intensification and formation. Recognized some gaps, and we've been working through various processes to try to fill those gaps with programs, instrumentation, development of capability, and within the region. So it's a campaign. It would be wonderful. I mentioned the Rutgers 100 and change. I mean, I think that would be a way to develop the campaign into a system so that there was a larger system brought to bear on the problems that we were trying to solve. So,
thank you. One premise that I was thinking about coming into the Q&A session is that I want to make sure I mentioned that I've been thinking about it, is we're all dealing with a challenge within the ocean observing world, I think, relative to others in terms of meteorology and even space exploration and travel, where we're dealing with the harsh environment in the ocean and we don't have the resources to do as much as we might want to do. And so there's often partnering and leveraging of multiple players. And I think in your case, Doug, there's a lot, including the Navy donating gliders each year and things like that, where you've got to work it as a team to be able to get something done in the first place to demonstrate success. So Paul, you next. I was going to ask, in the big picture, how do you see OOI fitting in as a system of ocean observing, or do you see it as a campaign or other?
Yeah, I think my answer would be both, probably, Carl. System comes to mind, but campaign, if the definition of campaign is that it's focused perhaps in time on a specific event or a specific region. There are elements of the OOI, for instance, on the cabled array, that's focused on seismic activity that occurs episodically. Other stochastic events around the Gulf Stream and eddies that spin off the Gulf Stream and come up across the Pioneer Array. Might be classified as more campaign type of information. But there's no doubt the long-term 25-year life of steady infrastructure operations, I think would also kind of qualify it as as a system of systems.
Thank you. And Lionel, what's working well or not in the system that you've been developing, and would you consider that part of a campaign or a part of a system or other?
Yeah, right. The overall objective is to develop definitely a system, and in order to do that, for now we have mainly had campaigns, and now in the second phase of the project, the objective is actually to turn this into a system for ConocoPhillips, to monitor the impact of their different activities around their oil and gas installation. We are as well, together with this Institute of Marine Research, part of the proposal, hopefully that will be financed next year, which is very similar to OI that was presented today, to turn this glider concept into one of these national system, and again with this concept of system, so that we can have deployed gliders for yearly observation for several years from now. So to turn this glider concept that we have developed into a system, that is the objective.
Do any of you have questions for each other? I've got lots more questions, so I can go, but feel free if you want to ask one of the other presenters. I guess, Lionel, I'm curious on ConocoPhillips as a customer, but then you mentioned the data getting to Copernicus. So I'm not sure if you said it in your presentation and I missed it, but I was curious, what's the business model in terms of the funding and then the sharing or not sharing of that data openly? Are you sharing all of that data, or is some of it not being shared?
Yes, I may have been unclear. For now, we are not sharing data with Copernicus, but everything has been defined according to the standards of Copernicus. So basically, our database on a click, can be, dumped into the Copernicus database. That's our intention. And there are some other databases as well where we can dump our data. So we're in discussion with ConocoPhillips with that, and I believe that at some point, once the project is closed and terminated, to make sure the data, don't slip unused into our database. The intention is to make them available.
Yeah, thank you. One of the things, this is probably for all of you, that I'm finding in working with partners across the spectrum of ocean observing technologies and trying to build, in the US, we're trying to build a system that's really system of systems, right? It's a network of networks approach in making the data available. And I was happy to see either CORTIDE, the quality assurance for real-time oceanographic data manuals that we publish in the US are getting used by Paul's group and others. And on the biological data side, I was listening to you, Lionel, talking about the EK80 sounder, and I've seen amazing work that's being done in multiple places in terms of using that technology in new ways. But then there's data challenges with that. So I guess, what are the recipes for success on working on a new technology and then handling of the data that you think are what's the recipe for success there? And maybe say something about the trade-off you think there is from picking a technology and standardizing and trying to stick with it versus adopting new technologies that are coming on all the time, and the challenge of change.
Yeah, that's a very good question. And there are probably different answers depending on the platforms, the gliders, or the sensors that people use. But for our own case, when it comes to using this EK80 and the Sailboy, the success for obtaining high quality data like we have boils down to having very good engineers. So identifying the right platform, making sure the sensors is integrated properly, and having into this platform, and having the capacity again to test, optimize, improve, and validate the sensor. And that goes along with having, of course, the scientists working very close to the engineer, when they looked at the data, to help the engineer to improve the integration of the sensor. Today, we are in some way, we've reached the second phase where in this first phase, we didn't have the data in real time with the EcoStandard. As you know, it generates a lot of data. But in the second phase, now we're going to have a portion of the data that will be online. And together also with Simrad, they are working on improving the onboard data processing. So we believe that within 1 year or so, we're going to generate the data online. We won't have 100% of the data, but that will be sufficient enough for us to understand what there is in the water column and to make assumptions, and also to have what I would call a smart sensor for improving the waypoints and the operation of the glider into the water column to really track what we're after.
Thank you. How about Paul and then Doug, kind of on a similar question? What recipe for success, and then the tension between adopting and standardizing a technology versus infusing new?
Yeah, I think if I could jump in, the luxury we have on OOI is we invested quite a lot of time in establishing science requirements that were then evolved into engineering requirements, which led to what instruments are needed to meet ultimately the science requirements. So we're driven more by the requirements than what's latest and greatest, which isn't to say that what's latest and greatest isn't evaluated. The project scientists across OOI are constantly evaluating new technologies, and where new technologies come forward, they're evaluated against those requirements, and we have a process to update those requirements if it's seen to add value. So there's a little bit of a methodology, I guess you'd say, to taking on a new technology, which has, I think, safeguarded us a little bit from going in too many directions without basis, or without necessarily a science need. Where we have identified and integrated new technologies, we take the step of integrating them on a test bed before deployment, and then deploying them for an interval, perhaps year-long, side by side with the existing technology. So I think those three things have been helpful to the OOI program: the requirements, test bed, and then the side-by-side deployment.
Thank you. And Doug, how about you?
Well, I think it's a little less important to what I was discussing because of, we're essentially a pilot project. So I'm not worried about that. What I would like to do is sort of take this in a direction that I mentioned, which was the decade for sustainable development, and the idea of ocean observing for developing countries and smaller economies, and making the point that there are so many opportunities with really rapidly advancing technologies, especially in data transmission and reduced cost and ability to do easier deployments, to do things like remote deployments, that I think those are important aspects that need to be explored in this decade for sustainable development. As we want it to be sustainable for all economies, for the places that really need ocean observations, we've got to look to some of these newer ideas. And I think that's an important point.
Yeah, I agree. I've been trying myself to imagine and figure out how we're going to do that under with the UN decade. I think that's a great idea. And then what's the doable do for using these technologies to support a developing nation that might need the observations, but then doesn't have even the IT infrastructure to necessarily receive the information in ways that we use it in more developed countries. We have in American Samoa, they've asked the Pacific Islands IE's partner to generate an email message with changes in wave height on the buoys, because that's the way that they receive the information most easily, because they often don't have wireless Wi-Fi connections. So they were able to at least identify a method that worked for them with the lowest common denominator. But that's interesting how that brings in constraints.
I mean, that's a little backwards looking. I mean, and so we want to change that to be forward looking, to say, what are the next generation of low orbit satellites that are providing internet, globally, and can we begin developing on using those platforms? I mean, as an, towards your example.
Yeah. And one of the things with the hurricane intensity questions, it's a major, I call it a team sport, because we've got so many players involved at different federal agencies, but also at different science and academic institutes. And we're, Paul, your gliders, we're counting if there's a hurricane near and there's an OOI glider, the data is available. And so if it's got temperature and salinity data near where a hurricane is, I call them other mission gliders that are available with their data. And it's incredibly important to share and cooperate. I guess, Doug, do you have a little bit more on the solution set idea, how we do that for the UN in the UN decade? Like how we organize to build the capability for the nations that don't have the ability now, but the technology is there now?
I mean, we're at the very beginning on some of these things, but even this idea of like this International Challenger mission, of bringing the idea of the importance of ocean observing to some of these countries and making it available, and doing more training and more, making the products available and usable so that countries can use them. I mean, that's the first step towards, then making the observations cheaper and easier and more available. So we're starting at the very beginning, which is sort of that socialization stage. I mean, as part of what we did in requesting clearances, we follow up with a visit, or we would have if not for the COVID, a visit to the country to present the data and explain what we're doing and how this is a useful, particularly in the Caribbean, we all want better hurricane forecasts, so how can working on this jointly improve that?
Yeah, and you should get credit for workforce development in terms of what you're doing in Ocoee with the U.S. Virgin Islands, and then Caracus with the University of Puerto Rico Mayagüez. They've got internships bringing students at the undergraduate level in to be a part of these pilot projects, so that in-water experience is happening at the undergraduate level. And those players are then applying for jobs within the IUS network within the US. And some of them are now federal employees in the Weather Service Office in Puerto Rico, for instance. So those are previous interns in the IUS network. So we're trying to figure out ways to bring in more diverse players from all walks of life into the work that we do, so that it's easier also to spread the word, which is a little bit of what you were talking about, Doug. So what do you, perhaps a question for each of the panelists. I'm looking at time here. We have about 10 minutes left. You're still able to ask each other questions if anyone has any. I haven't gotten any takers on that front.
I have a quick one maybe for Paul. I'm fascinated from a science standpoint of this idea of upping and moving the Pioneer array to another location. So I'm curious what sort of planning and thought has gone into that.
Yeah, Doug, thanks for that. I wouldn't say a lot of planning is going in. It's only being initiated now. It was always the intention that the Pioneer array would be deployed to its current location for, I think the time frame was 7 years, which will be up in another couple of years. So it's the NSF aim that they would lead a series of workshops and solicit input from the science community, probably by first providing what are the environmental constraints on the Pioneer Array. I don't think it would, for instance, work very well at a major river outflow in 20 meters of water, just as an example, because of very high current, very high turbidity, and very shallow. So establishing what are the constraints, I think, is on us to provide to help facilitate that workshop or series of workshops, and then to encourage the science community to think out of the box. For instance, I couldn't say whether it would have great science merit, but from an engineering perspective, the Pioneer Array could be put into one of the Great Lakes, for instance. It could be put pretty much anywhere around the coast. I believe the NSF, because it's a U.S. taxpayer organization, would expect the array to be redeployed around the U.S., but that includes Hawaii and Alaska as well, where it also could be deployed. I think for me, it'd be an exciting opportunity. We do have sort of 7 or so years of observation at the Pioneer Array site about phenomenon across the continental shelf break, the transfer processes associated with nutrients, physical processes associated with the eddies and what they transport and do to temperature profiles and so forth. So moving the Pioneer Array even a couple hundred miles north or south of where it is, or much beyond, I think presents with some exciting new opportunities to really establish a great baseline set of ocean observations from the fixed and moving platforms. So I have a question that I get asked, and I'm interested to know what Lionel and Doug might think. But the question is, what one kind of game changer technology that you're aware of that is being at least worked on today or is conceived of today, could significantly enhance your interests, be they scientific or communal, as yours are in part, Doug. And I'll start off with kind of the obvious one is for me is battery power, battery longevity certainly would help reduce cost and I think enable higher fidelity probably to the data that we're collecting by being able to power instruments to take more samples at higher rates. And then secondly, AI or intelligence on board, getting the intelligence closer to the instrument, less from shore. Glider piloting, for instance, still needs human in the loop. Also, oceanographic phenomenon that might be detectable in the middle of the night at one of our array sites on board one of the moorings, if there were onboard intelligence, it might be able to, in that instance, automatically ramp up or reconfigure its instrument sampling profile. So battery technology and AI would be my answer. Lionel or Doug, do you have any thoughts?
If I may, I can start. I think you named them all. Definitely, I'm in line with you. For my particular type of research, I see a lot of interesting development when it comes to optical sensor to look at zooplankton community. And one of them is now on the market. Another one is being developed together with some of my partners, and they are really interesting for, again, ground truthing the ecosonder data. And again, we will need artificial intelligence to look at this or to do this picture analysis, which often is very complex. So yes, artificial intelligence is needed, and also developing this smart sensor, having this onboard data processing to really select only the data that we are in need. I think this is for now where I see the most interesting part of the development, sensor to increase the number of functionality and application. So there is this optical sensors for zooplankton, but we're working as well with environmental DNA. I know when Barry has been working for many years on developing systems, to collect and to identify environmental DNA in real time. And we are working actually together with them to also have a system like this, a different system, but addressing the same thing. So environmental DNA onboard glider could help us again, to have, biodiversity at large, working with metabarcoding, but we can think as well of mapping maybe better specific species, which today, were mapped with basic sample or traditional sampling technique. Looking at invasive species, very often it's too late when we detect the presence of an invasive species, and I believe looking at eDNA can resolve this issue. Looking at toxicology, that's started to become a big issue in northern Norway. We see with climate change that toxicology events are moving north, and last year there was a loss of millions of salmon just because of this event. So we're looking at new tools to be able to detect this in real time, and that requires sensors, and especially smart sensors.
So yeah, quickly, Carl, right? I agree with all those, and the one that I brought up earlier, which is data transfer and communications, just the idea that we need to have the resources to bring the things that we take for granted on land, Internet of Things type capability to ocean. The ability to yes, collect that data with these new smart sensors, but then to distribute that around so that we've got a network of sensors and a network that can deliver the information to land-based users in order to take advantage of it. And that covers all kinds of things, including this, the idea of network sensors in the water, making intelligent decisions on where they go and what data they collect and what they transmit back. So I'm looking forward to seeing that take off hopefully soon.
Yeah, I'll just pile on here, and we've got about a minute left. So this was a great, Paul, you did a great job. I was thinking of a lightning round question, and that was a perfect one to give everyone a chance. I wanted to make sure to say thank you to Oceanology International for hosting this session, and to thank all three of you for contributing and presenting and participating in the Q&A. And to your question, Paul, I wanted to give a quick answer, which it's the same type of thing. It's sort of, for me, I think the edge computing and how we manage data, so getting more computing done at the sensor level, and part of that's parsing out the big data opportunity, what the little data solution is from that, and only using the bits and pieces that you need. And then artificial intelligence can help with that. We could get citizen science engaged and get people who care about mammals that need to be engaged with the ocean to help us sift through large data sets that might have mammal detection information in them. Or the HAB sampling we're doing in the west coast of Florida, for instance, on the beaches. We're using citizen scientists to do sample grabs for harmful algal blooms. So amazing opportunities there. So again, thank you very much. Any final words from any of you?
Thanks, Carl, for running the session. Very good.
Yeah, thank you. Yeah,
I look forward to seeing me in a few months. All of you.
Yeah, you all as well. So thanks again, Oceanology International, and signing off for today. Farewell.
Thanks. Bye-bye.
thank you.